And the result is exactly the the second part of the fundamental theorem of calculus. It says that if you consider a definite integral as a function of the upper limit, then the derivative of that function is equal to the function you are integrating evaluated at that parameter, at that variable. And so if you differentiate with respect to the upper limit an integral of the function x, f of x, so you differentiate with respect to t, the result is f of t. So the amazing thing about this statement is that it's very simple to state, although you will have to remember the formula, but the meaning of it can be expressed that you take a function, you start with the function f, and then you do integration of that function, and after that you do differentiation. And the result of that combination gives you the function back, exactly the same function. Right? So that means that differentiation and integration are inverse to each other in a very precise sense, like logarithm and exponential function. Right? You apply logarithm and then exponential, gives you the number back, or the other way around. Well, the other way around is a little bit more tricky for integration, but this way it gives you exactly f back. Although the argument changes, right? You started with seemingly f of x and resulted in f of t. But at this point we are talking about the function. And the function doesn't depend on the argument. Argument is a very artificial thing that we use to explain what the function is. What matters here is the function f. All right, so that's the obvious consequence of the theorem. And the second consequence, well, let me state the first as differentiation applied to an integral. F is f again. So these two operations are inverse to each other in this order, and of course we will have to check whether they inverse to each other in a different order. Now the second consequence is a very powerful consequence for the future. The consequence is that any function has an antiderivative. Which is not an easy thing to imagine. We agreed that any function in calculus has derivative. I mean, there are some exceptions, but in general, we expect the functions to have derivative. But now, think about this. If I tell you what the derivative should be, can you always find a function having that as its derivative? And the answer is yes, always. If I want f of t to be the derivative of something, what will that something be? Can you find g of t such that g prime of t is equal to f of t? And this theorem gives you the exact, precise answer. Right? You have to put g of t to be what? An integral from, let's say, 0 to t of f of x dx. And then derivative of this function with respect to t will exactly be f of t. And the detail that is very curious at this point, but not important for the future, is that for this to work, we only need the given function to be integrable. And to be integrable, it's enough to be just continuous. So if I give you a function, and the function is just continuous, and continuous means its graph has as many sharp corners as you want. And those corners means that the function itself, the function f, is not differentiable. But I can apply the integral, and what I will get back is a function that has derivative. And also that derivative is equal to my function. And my original function wasn't even differentiable. Right, so we will not go into details of that in the future, but it's just a curious point to notice. Alright, so basically now we have a precise way to anti-differentiate any function. Or at least we know theoretically that antiderivative exists.